Afternoon, grade 12s. Welcome again to Smart Teaching Online, proudly sponsored by VT Africa Holdings, Fibotech, and Vastra Tech. So in order for you to be part and parcel of today's lesson, you have to log into www.hellosmart.com. Take time to take part in the assessments. Sign up as a guest, type in your class ID, which is 598751. Add your name. So, grade 12s, yesterday we have started with the net work done. So today we have to continue with this so that we can finish it. Okay, if you can just look at yesterday's work, we talked about how are you going to get the net. I said we are just going to have different forces. Those forces will add up if they are in the same direction, or you can just take a difference if they are in opposite directions. Okay, denote this. This is very, very much important. Work done, denoted by W sub of net. We talked about steps to determine the net work done. We spoke about draw a force diagram of all the forces that are acting on the object. We spoke about the dot, which is the free body diagram. So if you can just look at this is a recap of things that we have done yesterday. The angle is very, very much important. If we are just going to look at the positive and the negative, this is step number 2. Determine the angle theta between each force and the direction of the displacement. Step 3, you have to use the formula of work, which is W is equals to the F change in X cos theta to find the work done by each force. Step 4, add the work done by each force algebraically to determine the net work. Okay, there are 2 ways that you can just use. You can just calculate the work done for each and every force that is taking part in the object. Now, there is another way that you can just do it. You can just calculate the forces. After the forces, you can just subtract or you can just add. The one that I showed you yesterday is part of this page. If you can just look at the step 1, draw a force diagram showing only the forces that act along the plane of motion. In other words, you're supposed to use a force diagram or dot or free body diagram. They can say use a free body diagram, you have to use that. If they can say use a force diagram, you have to think about all the object. You have to redraw it. You can just use a box to show the object so that you can indicate all the forces that are acting on that particular object. Okay, ignore perpendicular forces. All the time, you have to ignore the perpendicular forces. Perpendicular forces that I'm talking about, that is the normal force and the perpendicular work. All right, if you can just look at that, we have different steps. The second step, that's calculate the resultant net force. The net force is going to be denoted by capital letter F. That is the capital letter F, sub of net, acting on the object parallel to the plane. I tried to explain this yesterday. I talked about the parallel weight or parallel F of G. It's what I was just doing yesterday. Then it's what we are going to look at today. Step 3, calculate the net work done on the object using the net force. In other words, you have to add up or subtract to get the F net. It's going to be denoted by capital letter F, sub of net. Because of the capital letter F and sub of net, you have to Because of this, F sub of net, you have to use double sub of net, that is work, net work done, which is equals to the F net, F sub of net, change in X, cos theta. This theta here is the angle that we are just going to use when we do calculations. It's very, very much important as well. And then let us look at this example. Let us look at this example. Okay. How much work is done if a car of mass 1,500 kilogram produces a torque of 35,000 Newton as the car drives up a 30-degree slope for 50 meters? The coefficient of kinetic friction is 0.25. Okay. Earlier we spoke about this. The moment you come across with a question in physical science, you have to analyze it. You start with the given information so that you can just go to the unknown, what they are looking for. What is it given here? If we can just look at this, we have a car of mass 1,500 kilogram produces a torque. This is the force. The moment you come across with the torque, you must know that this is the force that the engine produced. That is 35,000 Newton. Okay, the car drives up 30 degrees. This 30 degrees is our theta. This theta played an important role because it's the one that is going to guide us. And what else? We have displacement, which is 50 meters. And what else? We have been given the value of the coefficient of kinetic friction. Coefficient of kinetic friction, this one is, let me extend my page, is a mu. That is why here we have, remember, in grade 11, you have done frictions. We have kinetic frictions, we have static frictions, but this time, because this one is moving up, we can talk about the kinetic friction. That is denoted by small letter f, which is equals to mu capital letter N, which is the normal. Okay. Now, we have to write down the data all the time. When you approach each and every physics question, you have to write down the given information. Okay, let us start with the given information. Here, I can just write data. What do we have there? We have the mass of an object. The object there is car. We have mass. Let me write in capital letter. Let me write in capital letter. We have capital letter M, sub of car, so that we can just know what we are talking about. It's 1,500 kilogram. And what else? We have F. That is force, applied force, which is equals to 35,000 in newtons. And what else? We have been given theta. Theta is equals to 30 degrees. And what else? We have been given, let me extend my page. We have been given Displacement, change in x, which is equals to 50 meters. Okay, and what else? We have mu, coefficient there, that is mu, which is equals to 0.25. Okay, what else? We have been given, they need us to calculate the work, which is W, which is unknown. Okay, what I'm going to do, while I'm busy working out here, I need you to work out as well. Okay, if we can just go back to our object. The object is here. We have a force, that is upward force. It's what we have here. And then because of the coefficient, we have been given that the coefficient of kinetic friction. Now we know that the coefficient here is for kinetic. In other words, we're just going to have something coming down from there. It's where you can just talk about the f of k, because it's always opposing the direction of the movement of an object. Takes the other direction. If the object is going upward, then the kinetic friction will just go down. All right. Now, this is what we have. This is what we have. This is what we have. We have to calculate this. I told you that we have to start with the first step. You have to show all the forces that they are acting on the object, all the forces that are acting on the object, all the forces that are acting on the object. If you can just look at this, we have a normal force. A normal force here has been indicated by capital letter N. This is your normal force. It's going upward. In other words, it's perpendicular to the surface. All right, we have this torque, F applied, is just pointing upward. Okay, we have this F parallel here. Yesterday we talked about F parallel. We talked about W parallel. Now we have two things, because we are aware that we have a friction. We have a friction that is taking part here. We have to show it. If you can look at that, we have a friction here that is pointing. It's opposing. That is F of K. This is F of K. It's where the contact happens. If you can just look at the object, you look at the object, you look at the surface. Now we have this friction that is happening on the surface. That is why I'm saying we have this F of K, where the tires are. Okay, if we can just look at that, we have F there. It's happening there because it's just trying to slow down the motion of this object. Okay, now we have to look at the weight. This is your weight. Weight all the time is the one that is pulling the object downward all the time. Why? Because of the gravity. Because of the gravity. If you can just look at this, I will show you soon about why we have this W all the time pulling the object downwards. Okay, we have the gravitational acceleration. All right, now we have to look this here. We have F we have F parallel, F perpendicular. Sorry, not parallel. That is F perpendicular. If you can just look at that, how are they coming up with this? I tried to explain to you yesterday to show you how they came up with 30 degrees. Up here, if you can look at it, we have this dotted line here. It's parallel to the surface. We have this F parallel, also parallel to the surface. If you can just look at this F of K, it's just on the surface. It's happening on the surface. Now we have to know how are we going to substitute this. Let me extend the page. Let me show you, even though you are just going to have this formula sheet at the back of your paper. Let me write down the formulas. F parallel. F parallel is equals to, that is W. That is W sine theta. Okay. The other one is F perpendicular, which is equals to W cos theta. If you can look at that, we have F parallel. We have F parallel and F perpendicular. F parallel, it goes with sin theta. You have to revisit trigonometry mathematics, how we reach here. And then F perpendicular, also trigonometry. You have to look at the triangle, and then it's going to give you, because cos theta is equal to adjacent over hypotenuse. Okay. If you can just look at this, we have these two, but what is the formula of W? We all know that weight, let me write here, weight is equals to mg. Your g there is the gravitational acceleration. Gravitational acceleration. Gravitational acceleration. Okay. If we have this, we know that we can just substitute W with mg. Wherever you see W, you have to go there. Okay. What about the F of K? F of K, in previous page, we said F of K from grade 11 is equals to, this is the product of mu and the normal force. And the normal force. Okay. We are not yet done here. Let me extend the page. And we have normal. If you can just look at that, we have normal here. That normal, it has, is, if you can just look at it, we have this F perpendicular and there. This is the normal force. This is the force of the perpendicular to the surface. Now they are equal. They are in different directions, but we have to show. Okay, in other words, N is equals to F perpendicular. And we know that F perpendicular up there is equals to W. In other words, therefore, N is equals to mg. If you can just look at that, we have W cos theta. I have substituted W by mg. Now we have cos theta. Cos theta. Okay. Now it will be easy for us to calculate. If you can just look at that, we can just substitute our normal force where the equation of kinetic friction is. We can just substitute our N with mg cos theta. All right, let me do that. Therefore, F of K, of sub of K, which is equals to that is mu, and then mg cos theta. If you can just look at that, now we have the formula of kinetic friction. That is kinetic friction, and we can just go back and look at the diagram. Okay, if you can look at the force diagram, then this parallel and F of K, they are downward forces. These are just going downwards. If you can just look at the applied force, is the one that is going upwards. Okay, now we have to, let us do this. Let us do this. Okay. Let us calculate. Let us substitute the values here for F of K before we went to F parallel. Okay, if you can just look at this one, we have mu, and mu is given is 0.25. Is there any unit there? No, we don't have a unit. What I'm going to do, I think I can just take it back here. Let me take it back so that it will be clear. Okay, F of K, or sub of K, which is equals to mu, that is mg cos theta. Cos theta. If you can just look at it, we are just going to substitute the values. This mu is given 0.25, 0.25. They didn't give us the unit of mu. Why they didn't give us the unit? It has no unit because it's a ratio. It's a ratio of forces. It's a ratio of forces. If you can look at it, normal here is a force, it's a normal force. Even here, we have what? F of K is also a force. In other words, that is the Newton divided by Newton. You don't have any unit at all. That is why we have this 0.25 without a unit. Okay, now we have to look at the mass. Mass has been given. The mass of the car has been given. It has been given. It has been given 1,500, 1,500, 1,500. We extend it. 1,500 in kilograms. And then G there, gravitational acceleration is approximately 9.8 meters per second squared. That is the gravitational acceleration. It's very, very much important. You have to do that and then multiply by cos theta. There it was 30. Okay. Theta there is 30. Can you extend it a bit? Is 30 degrees. Okay. If we can look at this, we have managed to substitute the mu, m, g, and theta. Let us calculate. Just use your calculator. Just use your calculator. Just use your calculator. We have 0.25 multiplied by 1,500 multiplied by 9.8 multiplied by cos 30, which is 3,182, comma 6. In what? In newtons. Remember, we were looking for kinetic friction, which is 3,182,6 Newton. All right. Now we have kinetic friction. What about the parallel? What about the parallel? Now, if you can just look at these two, all of them, they are pointing downward. They're just pointing downward. Let us calculate the F parallel. Let us calculate the F parallel. Now, we have to calculate F parallel. That is upward, is downward, sorry. This is the force pointing downward. Now, F parallel, which is equals to, we have a formula. We have to go back to our formula, which is W. I'm going to substitute W with mg. That is mg. That is mg sine theta. Okay. That is mg sine theta. Let us go back. It's W sine theta. Fg parallel. Okay. Now we have to substitute the mass of an object. Mass there is 1,500 in kilograms multiplied by gravitational acceleration there, which is 9.8 in meters per second squared, multiplied by sine 30. Your theta there is 30. Okay, if we can just look at that, we can just continue here. I need you to calculate with me. We have 1,500 multiplied by 9.8 multiplied by sine 30, which is 7,350. 7,350. In what? This one is going to be measured in newtons because we are just calculating the force. Okay. Now we know all the forces, the values of all the forces that they are acting downwards. Okay. The total. Let me just write downward forces. Downward forces, which is equals to, we have a total. In other words, we can say F total downwards, which is equals to the F parallel plus the kinetic friction, which is equals to, we have to add them because they are, if we can just look at the force diagram, all of them, they are pointing in one direction. That is why I'm adding these two. Okay. After that, I have to say whatever that you got as a force parallel there is 7,315, which is 7,315 Newton plus, what do we have there? Is 3,182.6. 3,000. Is it 3,000? 182.6. It's also in Newton. Okay. It's not very nice. Let me write it nicely. $3,182.6 Newton. These are the forces acting downwards. They are opposing the motion of an object. What are you going to get there? If you can just add up. $7,350 plus 3,182.6, which is equals to 10,538, 32, not 38, 32.6. This is Newton. Okay, if you can just look at this, this is the total of all the forces that they are opposing the motion. Okay. Let us calculate all the forces that are pointing upwards. It's only the applied force. It's only the applied force. Only the applied force. Downward forces. Upward forces. Upward forces. We have only this applied one, which is equals to, let me check for it. Sorry, we have to look at that. That is 35,000 Newton. 35,000 Newton. That is 35,000 Newton. 35,000 Newton. 35,000 Newton. It's 35,000 Newton. Okay, let me extend it. If you have these two forces, it's where you can just get the net force. In other words, you have to subtract. We have to say F sub of net, which is equals to F A minus F total. It's what we have there. F total is coming from all the forces that they are pointing downwards. Okay. Let us substitute this. We have 35,000 newtons minus F total, which is 10, which is 10,532, 5,032.6 in newtons. If you can look at that, you are just going to get the following. 35,000 minus 10,000, 532.6, which is 24,467.4 in what? In newtons. Okay, we got our net force. Because of this, we're not yet done, because we have to calculate the net work done. Earlier, I spoke about this net. It's represented by capital letter W sub of net, which is equals to, that is the net. F of sub of net, that is the net force. Change in X cos theta. This is the formula of work done. Since we started with work, we're just using this formula. All right, now we have to move forward. Because of this, we have to substitute all the values of F net, change in X, and cos theta. A theta there, we know that is 30 degrees. Now the F net is 24,467.4 in newtons. This is very, very much important. Let me, okay. It's not that clear, because let me, okay. We have to say this is equals to 24,467.4 in newtons, close bracket, open bracket for our displacement. Displacement is 50 meters. Our displacement then is 50 meters. Let me extend it. That is 50 meters multiplied by cos of 30 in degrees, which is equals to, take out your calculator. Let's just do this together. Okay, 24,467.4 multiplied by 50 in meters multiplied by cos 30. Cos 30. If you can just look at that, is that is 105,946,9. Let us leave it there. in joules, which is equals to, this is the same as, you can say, this is the answer of what we were just looking for. This is the answer of what we were looking for. I hope you just got what I got here. All right. Okay. Let us move fast. This is how it is done. 50, that is cos 0 minus, let me check. The angle there, cos is too much. I see it's true. We have to use angle 0 because we are dealing with the x-axis. We are going to use 0 here. Beg your pardon, that is 0 in degrees because it's a straight line. Because it's a straight line. We are dealing with the x-axis. Beg your pardon. I made a mistake there. It is 24,467.4 multiplied by 50 multiplied by cos 0, which is equals to 1,000. 1 million. It's 1 million. That is 370 in joules. Okay. I beg your pardon there because we are dealing with the x-axis. We have to ignore the perpendicular. I decided to use the angle there for the perpendicular. Okay, this is the answer. And now, due to time, I can just give you a homework. That is the homework. This is the homework that I'm giving you. Okay, use drawings to help you to solve this problem. A skier is being pulled up a 20-degree slope by a drag lift. The pulling wire is at an angle of 15 degrees to the slope, and the forces acting on the skier arm. The first one, the pull of the drag lift wire, P is equals to 32 Newton. The second one, the perpendicular contact push of the snow, which is denoted by N is equals to 620 Newton. Then the third one, the frictional push of the snow, F is equals to 53 Newton. And then the last one, the pull of the F, that is W, which is equals to 750 Newton. This is the following, statement true or false? In other words, you have to calculate for the first one that whether you're going to get it 0.93 or not. The second one, to calculate, remember for perpendicular, we spoke about each and every angle in perpendicular, which is 0. That is 0 degrees. If you have 0, you have to make sure that your theta is equals to 0 in 90. Your theta is equals to 19, and calculate and see if you are going to get the work done of 0. And the other one is the frictional push. You have to calculate all of them until you get this answer. If you can't get this, you have to say is false, or you can say is true. If you can just look at that, time is up. I can just give you the answer. The answer here is your A, but I need you to do that. 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 If you can just look at the answer is A. What I need you to do, you have to do all the calculations to confirm that the answer here is A. Thank you very much for being part of today's lesson. See you next time.